Welcome to this class, and today we'll be looking at hardware, mostly computer hardware, and also we'll look at how a computer essentially boots. So we'll be going into the details of XV6 and look at touch a little bit on the source code of the booting process in the XV6 operating system. Okay, so when we are talking about hardware, computer hardware, so as I did mention, you could have a computer which is a desktop and laptop, as we all know, but you could also have a computer, uh, a system or electronic device with a CPU, memory, and which acts like a computer, from small embedded devices to large servers, right? So especially in the small embedded systems, this particular file shows how the system is organized, right? For larger systems like your desktop, your laptops, or servers, it would be more or less similar, but there would be certain differences as well. To keep things simple, we'll just look at the structure or the organization of a system, especially focusing on an embedded platform. Okay, so critical in the embedded system is the CPU, which is the central processing unit. And as we discussed in the previous videos, so you would have one or more processor cores, which essentially forms part of the CPU, right? Now, these processor cores could have a single hardware thread or multiple hardware threads. So, any program that you execute in this in your system essentially comprises of instructions which get executed within this particular CPU, right? Now, the CPU essentially has several inputs and outputs, and critical among them are the reset and the clock, right? So, the reset vector, the reset essentially is a signal which typically looks something like this. It would be a pulse, which essentially tells the CPU that it needs to restart, and the CPU goes into some initialization mode. The clock, on the other hand, is a sequence of pulses of this particular form, right, which essentially is used by the CPU and also the rest of the system to perform various activities in different uh, intervals of time. So, for instance, at every rising edge of the clock, the CPU, the transistors, gates, and other hardware present in the CPU performs various operations within a specific clock period, right? Now, many CPUs essentially have something known as the memory management unit, or the MMU, which is essentially highlighted here because it's a very critical component when we speak about operating systems. Also closely coupled is the cache memory. So it's not very visible to the OS, unlike the MMU, or not very important uh, for the operating system. Okay, it's not very important for the functioning of the operating system, but it's critical to essentially boost the performance of the of programs, right? Now, outside the CPU is what we call as a system bus, right? So that there are several standards for the system bus in the embedded environments, such as when you have a processor such as ARM or the RISC-V processors, then typically the system bus is based on a standard which is called AXI, right? And the system bus is essentially a set of connections which come out of the CPU. It comprises of a large number of such connections and are used to essentially connect various modules to the processor. So, for instance, you would have your USB controller, which is used to connect any USB device like a keyboard or a mouse to the CPU. So, for instance, if I essentially connect a keyboard to the CPU, it would be connected through the USB port, and any keys that gets pressed on the keyboard would pass through the USB controller and then enter into the CPU, right, where it's then processed. So similar to this, your system could have um, various other such peripheral modules, or as we call it as IO modules or input output modules, such as network cards, display controllers, as we see over here. Also, another example is the UART, which is the serial interface. So the UART stands for Universal Asynchronous Receiver Transmitter, which is a very and possibly the one of the most simplest interface present in a computer system, and it essentially could transmit or receive a single bit at a time, right? You also have secondary storage controllers. So a secondary storage controller, as many of you would know, is then used to get connected to your hard disk. For example, a SATA hard disk or a flash disk essentially gets connected to the CPU through the secondary storage controller, right? Now, a very critical aspect for any program to execute is the aspect of memory. And there are multiple different types of memory that are present on a system. You could have volatile memory, such as DRAM, which is dynamic random access memory. So any of your program data, the stack or the heap of your program is going to reside in the DRAM. Also present is read-only memory, which typically has the initial portions, which is typically much smaller, and has some initial portions of the of programs which first get executed in the CPU, right? So, for instance, when your CPU starts up because of a reset vector pulse, it first starts to look into the read-only memory for programs and instructions to execute. So later on in this particular class, we look at how the CPU essentially fetches these instructions from the read-only memory and begins to execute them, right? From an operating system perspective, another important peripheral is the interrupt controller, right? So the interrupt controller essentially could send signals to the CPU to interrupt its execution. So aspects such as timers or any other device, if it wants the CPU to have, or if it wants to send an event to the CPU, it is sent with the help of these interrupts. So just to take an example, let's say we have a keyboard connected to a USB controller, and when a key is pressed, this keystroke would then interrupt the CPU, and now the CPU knows that it needs to read the keyboard and identify which key has been pressed, right? So many of the peripherals uh, communicate with the CPU through interrupts, right? And as we'll see later on in this course, interrupts form a very critical aspect for operating systems. It is used to ensure fairness of execution of different applications, or as we seen in yesterday's in the previous class, the process execution and so on. Okay. Now, with all of these different peripherals, memories, and interrupts and so on present within a computer system, or in this particular case the embedded system, one critical aspect that is important for the CPU to communicate with each of these different modules independently are addresses. So there are two types of memory addresses, right? So these are memory addresses that are present in the RAM or the read-only memories, like the flash memory. But there are also another form of addresses which are used to communicate with the I/O with the peripheral modules like the UART, the display controller, and so on. So such addresses are called memory mapped I/O addresses. So anything that the CPU does on the system bus is always linked with one or more addresses, right? So just to give you an example, the system bus. Okay. So just to give an example, the system bus has something known as some address lines, which are typically, so these addresses generated by the CPU are placed on the system bus on these address lines, and based on the CPU there could be typically 16 or 32 or 64 bit such 64 bits of such address lines, right. So if there are 32 bits of address lines, it indicates that the CPU can address um, different components from in the range of 0 to 2 power 32 minus 1, right. Each of these addresses can be assigned to one or to exactly one of these different peripherals, right. Now the way this range of addresses 0 to 2 power 32 minus 1 is essentially organized is called the memory map. And yeah, so here is an example of a memory map. It has addresses ranging from 0 to FFFF to 8 Fs, right, which is essentially 2 power 32 minus 1, right. So the CPU can generate addresses in this particular range, and each address it generates could possibly be directed to one of the different peripherals or one of the memories. So for example, if the CPU puts on the address bus or the address lines the value 0x8001, right. If on the address lines this particular value is essentially put, it is essentially directed to the DRAM because this address lies within the range of the DRAM, right. So in this particular memory map, we have a small RAM of just 256 megabytes, right. And depending on your system, whether your system has 512 megabytes or 1 terabyte or things like that, this range of addresses would essentially differ, right. Now besides the memory, the DRAM, and here is the boot RAM, that is the read-only memory. Every peripheral essentially would have certain set of addresses within this entire memory map. So, for example, you would have say your mouse to have a 256 addressable ranges within this particular region. You have your interrupt controller to take another 256 bytes starting at this location 20 million and so on, right. Here is another example like 0xa followed by 3 zeros then 4000 essentially indicates the UART. So what this means essentially is that if your CPU sends out an address on the system bus with a value which is within this range 0x8 3 zeros followed by 4000 to this value plus 256 bytes, it would the address essentially would indicate that the UART that it is trying to communicate with the UART, right. So let's look at what exactly happens taking the UART as an example. So remember again that the UART's addressing starts from this location 0x A000 4000, which we call as the base address for the UART, to this base address to so this is the start address or the base address for the UART to this address plus 256 bytes, right. So if any address is put by the CPU on the address lines that falls within the range, it essentially enables the UART to be active, and the UART is expected to communicate back to the CPU, right. So let's see how these addresses are essentially useful. Okay, so So, what we have here is some set of registers which are present in the UART controller. Now, if I go back to this slide, what it means is that within this particular UART, there are a set of registers which are defined very specifically for this UART module, right? So, there are not too many, but there are, as we see over here, it's just 6 different addresses, and these addresses, each of these addresses can be accessed, each of these registers can be accessed by the CPU, right? So, for example, at the address 0x4 A 0004000 is the register name called baud, right? So, this baud register is of 16 bits and is essentially used to configure the speed of communication of the UART, right? The speed of communication, because this is a serial communication, so the speed is essentially in bits per second, right? So, setting a value appropriately in this particular register can be used by the operating system to configure the speed at which the UART can communicate, right? Now, there are two more registers, TX and RX, which are actually important for us. Now, TX essentially has an address 0xa00040004, right? In other words, it's 4 bytes ahead of the baud, right? So, what does this mean? So, notice first that this address is within the range of the UART, right. So, the UART starts at this address 0xa000400 plus 256 bytes from this location, and the TX register is just 4 bytes away from the baud register, right. So, how is this TX register actually used? So, whenever the CPU wants to transmit some data through the UART, right. So, whenever the CPU wants to transmit some data through the UART through the serial interface, that data is essentially written in the TX register, right. So, so any data, so let's say I want to transmit some sequence of binary bits, right. So, corresponding to these binary bits of maybe 8 bits at a time or 32 bits at a time, the CPU would write these binary bits into the TX register, right. Now, the UART controller reads the data present in the TX register and sends this data bit by bit over the serial interface. In a similar way, we also have an RX register, right. Now, the RX register corresponds to the holds the received data, right. So, it is present at the address 0xa004008, right. So, what does this mean? Any data that is received by the UART controller through the serial interface is essentially stored in this RX register. So, what the CPU needs to do is that it could just load this address on the address lines in the system bus 0xa00040008, and this would be a request to the UART controller to send the data which is present in the RX register. So, in other words, any data received stored in the RX data would now be put on the system bus and transmitted to the CPU. Okay. Now, in addition to this, we have other registers like the status register, the control register, and the enable interrupt register, right, and their functionality is kind of similar to the other to the baud TX and RX, right. So, the status, for instance, is used by the CPU to identify if there was a problem or if there is an error that has occurred during the communication through the serial by the UART controller. The control register is used to enable some kind of communication protocol, to enable error correction and things like that, right? So this piece of code shows you what happens at the OS. So it's a very, very simple piece of code which shows you how the operating system would be able to interface or communicate with the UART controller, right? So first of all, notice that we have a hash defined UART base to be equal to 80x A004000, right? So this is your base address for the UART, and at different offsets of 0, 4, 8, 12, 20, 24 bytes, we have different addresses that are different registers that can be accessed, right? So here are just two functions that would be executing in the operating system, very specifically within the device driver component of your operating system. So this device driver would be for the UART, which is used to initialize the UART, and the read underscore UART function is used to read the data from the RX register into the CPU, right? So let's look at the init UART. So this is highly simplified, and what you see over here first is a pointer, a memory pointer called baud underscore reg, which is initialized to UART underscore base. Notice that UART underscore base is 0xA004000, which is corresponding to the baud register, right? Now, so what are we having over here? So we essentially have a memory pointer which is pointing to the UART base, right? Now, this particular statement star baud underscore reg equal to 0x70 is essentially writing this value of 0x70 into the memory location pointed to by baud underscore reg, right? Now, the memory location pointed to baud underscore reg is essentially the baud, the register name called baud, which internally means that this value 0x70 is getting written into this baud register. So what is the implication of this? The init underscore UART function, which runs from the device driver of the operating system, is setting the baud rate or the communication rate for the UART controller to essentially work, or the speed with which the UART controller has to work, right? So just to make things clear, we are defining a memory pointer called baud reg, and we are making it point to this location 0xA004000, which happens to be the register called baud, which is present in the UART controller. So anything, so if I do something like star baud underscore reg equal to 0x70, essentially it would mean that you're storing the value of 0x70 into the baud register, right? Now we have the second function called read underscore UART. Okay, so read underscore UART, we are actually using two more registers. One is the RX register, which is present at an offset 8 bytes from the base register. So so you can actually observe how we make this particular memory pointer, which is of 32-bit U32, defined as RX underscore reg. We are making it point to UART underscore base, that is our 0x8000 A0004,000 plus 8 bytes, right? So 0xA00 plus 4 bytes essentially is our RX register, right? So we also define another 8-bit value, which is U8, stands for the unsigned 8. So U8 is an unsigned 8 because of the star. It's an unsigned 8-bit pointer. or in other words an unsigned character pointer, which is pointing to status underscore reg and initialized to this particular address UART underscore base plus 12. So this corresponds to from the base address an offset of 12 bytes, and this essentially is status, right? In other words, status underscore reg has the address A000400C, right? While rx underscore reg essentially has the value 0xA00040008, right? Now the last two statements essentially are reading the value of the Rx register. The way this is essentially working is first with a while loop, which is continuously polling the status register and specifically looking for the second bit. So notice that when we do star underscore reg, star underscore status reg, we are essentially reading the value present in the status register, right? The status register is present in the UART controller. So every time we do star underscore reg, it results in a load operation from the status register present in the UART controller into some register or into the CPU, right? And within this within the status register, we are ANDing with 0x4, right? The reason we are doing that is that the second bit, the least significant bit is the 0th bit. From there, the second bit essentially indicates whether some data is being stored in the Rx register or not. So when the UART controller receives data through the serial interface, it stores it into the Rx register and sets the second bit in the status register, right? Therefore, while polling this particular bit in the status register, one can indicate if there is some new data that has been received or not. So if some data has been received and stored in the status register, then we essentially do a star rx underscore reg, which is essentially reading the rx register. The received data is essentially read with this particular command star rx underscore register and returned by the function. So what you are essentially seeing over here is that within this particular function, it will continuously loop, continuously wait until the UART controller has received some data, stored it into the Rx register, and then we read the Rx register and return back the value. So notice that we are returning this U32, indicating that 32 bits have been read from the UART controller and taken into the CPU for further processing.